Hello, everyone. My name is Lima, and I'm a systems engineer at the Linux team at Cloudflare, and I'm joined today by my colleague Matt Flemming, and we will be talking to you today about how we are currently serving millions of boot artifacts to allow all the machines in the Cloudflare to boot um, within this infrastructure. So. Uh, as I said, I'm João Lima, and I was previously a product security engineer at VMware, and I've also been part of the infrastructure security team at Cloudflare. And I'm interested in operating system security and cryptography, and I've worked in several projects in both of these areas at both companies.
Hey everyone, I'm Matt Flemming. I work with Joao on the Linux team at Cloudflare. I'm a former Linux kernel maintainer. I was the maintainer of the EFI subsystem for a number of years. And for the past decade or so, I've really focused on performance of systems, so operating systems, databases, and distributed systems. And I've co-authored a couple of papers in this area, one on change point detection for performance analysis, and another on testing distributed systems. So the presentation today is going to be broken into 4 parts. First, we're going to look at Cloudflare's fleet architecture, how the fleet is designed, and how we can categorize the machines inside of it. Then we'll talk about the boot process, so how we boot an individual machine within the fleet. Then we'll cover some of the design choices that we made and how they've evolved over time to improve security and scale. And finally, we'll wrap up with some ideas for future work, things that we're currently working on, and places we want to go to further increase security. So Cloudflare operates at a pretty large scale. It has co-location facilities in over 300 cities around the globe. And those colo facilities can be categorized into 2 groups, basically. So we have the edge and we have the control plane, which is sometimes referred to as the core. The control plane colos are very dense, and they have some over 3,000 machines. And the edge is different in that we have many more co-location facilities that are classified as edge, but the density is much less. Usually a few hundred machines operate out of those locations. For historical reasons, you may see the nodes referred to as metals throughout the rest of this presentation. And to let you in on a little bit of Cloudflare lore, the reason for this is historically, the engineers needed some way to distinguish between the physical machine running the services and the virtual machine running on top of the physical machine. That distinction's dissolved over time. We still have virtual machines, though not as many, but the name metal, which is for the physical machine, has stuck. Cloudflare uses a stateless operating system. So though we run a Linux kernel with a Debian distribution, everything is run out of memory, and we don't persist any of the operating system state to disk. Obviously, for services that require state, such as database services and things like that, they do have access to a local storage. But the operating system is best thought of as being completely stateless, which allows us to reload the operating system state on every reboot of the machine, and really helps with the dynamic environment inside of Cloudflare, which I'll cover in a couple of slides. We also make extensive use of secure boot to verify that the kernel code and the kernel modules that we're running are of known origin, and that we can verify that the code is the code that we think it is. So the colos can further be classified into metals and DM nodes. And the DM nodes are data center manager nodes, which serve a special purpose inside each of the co-location facilities. DMs are responsible for serving the boot artifacts that are used by the individual metals to boot. So kernels, RAM disks, and diagnostic tools, things like that, and firmware images too. The DM allows dynamic configuration of which artifacts are served to which machines. They are rendered locally on the DM and served over Nginx. So the metal will make HTTP calls to the DM to receive these boot artifacts. And each of the artifacts is cryptographically signed and then verified on the metal as it boots. So broadly speaking, at a very high level, the boot process for each of the metals kind of looks like this. You have power sent to the machine when you power it on, the chipset and the CPU initialize, memory gets trained, then we jump to the firmware, which executes and launches iPXE. iPXE is used to fetch the boot artifacts from the DM, which are then cryptographically verified. We boot into the kernel, modules, and finally into user space. A note on the secure boot keys. So when a metal is initially installed into a colo, the secure boot keys are provisioned and locked down so that we can verify all the code that's running there. And as I mentioned, iPXE is used to pull the images from the DMs, and we rely heavily on the secure boot chain for security. This is an image of a pre-rendered iPXE script that is used to boot a metal, and it allows us a lot of configuration and dynamism as well. So using this flexible scripting language, we're able to do things like not just tailor which kernels boot where, but also like run kernel experiments, kernels with specific patches in specific locations and for specific metals. So it's a very powerful method of serving up these boot artifacts. And with that, I'll hand over to Joel.
Thanks, Matt. So as Matt was just mentioning, we are a pretty heavy user of Secure Boot, and we rely on it pretty extensively to guarantee the security of our fleet. And looking at the previous boot process graph that Matt showed, we can see like UEFI Secure Boot is used from the moment we have firmware running. It's used to protect the EFI binaries that are loaded by the machine. In this case, it's used to guarantee the integrity and the authenticity of the iPXE environment that is loaded afterwards. And by chain, it's used to guarantee the integrity of the kernel. However, if we look at the earlier portion of this chain, there is still some gap to be addressed here, and we have done that a few years ago. You can read more about that on the blog post that is linked in this slide. But essentially, it's an additional secure boot mechanism which we call platform secure boot, where the CPU itself is configured with the certificate it must accept, and the firmware, the UEFI firmware, is required to present the signature before it's allowed to execute. And in this case, we guarantee the integrity of the firmware itself and establish a chain that is rooted in a hardware component. However, if we take in consideration that we are using iPXE as our boot scripting environment, there are still a couple of blocks that are not covered by UEFI Secure Boot traditionally. And in this case, that would be iPXE scripts themselves and all the artifacts that are used by the kernel to build a user space environment. So all the initial RAM disks are not covered by UEFI Secure Boot. And to address that, we rely on a mechanism provided by iPXE, which allows each artifact to undergo signature validation before it's handed over to the next stage. So this way, because we are guaranteeing that the iPXE environment itself has its integrity validated, we are guaranteeing the rest of the chain that we were not guaranteeing so far. So in terms of boot strategies, the outline of the boot process is always the same. It's exactly what we have shown, but the strategy we use to retrieve the boot artifacts may vary depending on the node or depending on the situation. So the first and more used strategy is network booting through the VM. So in this case, we retrieve the artifacts just in time when the node, the metal, the DM is booting from a DM that is serving the primary role for that collocation at that point in time. An additional strategy, which we call local boot, is to use artifacts that are stored locally on disk in a special EFI partition. If you think about it, it's kind of a chicken and egg problem. So before we have a DM, we still need to be able to boot the first DM. So this is our way out of this cycle, and it's used to boot the first DM as the default strategy. On the other hand, if it happens that we have a colo with no DM available, which is not something that happens very often, but may happen in the smaller edge colos, we use local boot as a fallback strategy to boot metals. So the main difference here is, rather than getting artifacts just in time, the boot artifacts stored locally are synchronized every time the configuration management runs, which in our case, it's about every 3 hours. So in terms of architecture, and if we separate boot into two different flows, we have the boot render flow, where the primary DM prepares all the artifacts to be consumed by all the machines in the colo. And then we have the boot flow, where the nodes consume the boot artifacts that have been rendered and generated before. So there is a separation between rendering and actual use of those artifacts. So while this architecture has given us like an adequate level of protection, it was just like a first step in a longer journey. So now I would like to talk to you about the next stage of this boot infrastructure and what we've been working on for quite some time now. Some of the challenges that this architecture presented to us have been that, first and foremost, we have to trust too many nodes to render and sign boot artifacts for our fleet. So right now, if we go back to the boot flows, we have all DMs in our fleet rendering and signing the boot artifacts that they will be serving. Ideally, we would like that set of trusted entities to be as small as possible. If possible, just a single entity rendering and signing these artifacts for us. So the second challenge is that DMs do have a failover when we have more than one DM in a colo, but in any case, the failover is not really elastic. So we are generally bound to the capacity of a single DM there. And also, not least important, is that currently the configuration management update time is largely dominated by boot artifact handling, and sometimes to no good reason. And finally, the local boot model that I was just described is also costly and inefficient, because we are polling and checking every time if there is an artifact update to be included, even if there wasn't an underlying change on the data to that node. So to further guide the next step of this design, we added a few additional requirements, and one of them is that this system must be able to generate artifacts for all nodes in the fleet, as opposed to the model we have today, where each DM only generates and signs artifacts for the nodes in that specific colo. A second requirement is that this service needs to be highly available. So if you follow Cloudflare closely, you know that we've had availability incidents before, and even though we've been working very hard to make sure those never happen again, we want the service, which is a critical part of our infrastructure, to be highly available and resilient to that type of failure. While doing that, we do accept some degradation in the guarantees we provide. So we may not provide absolutely the latest version of every boot artifact for each node, but we guarantee that we provide a bootable environment to any node in the fleet, irrespective of the control plane being available or not. So the architecture we ended up landing on is this architecture I'm showing you. So we have the boot service is running on top of Kubernetes clusters, and we have like a primary backup architecture to it, where we have two different clusters working behind service discovery, and that they exist in different geographical locations, and they guarantee that for most failures we will be able to still handle boot artifact requests through our Kubernetes infrastructure. And on the other hand, for artifacts that we know shouldn't change in between requests, we allow them to be served directly from S3 clusters, and to that effect, we keep the signatures alongside the artifacts and serve them from S3 whenever they are available. With this design, we are able to provide a relatively reduced trust domain, in the sense that only the boot service has the capacity to render and assign dynamic artifacts to nodes, and on the other hand, we do provide static artifacts from S3 storage, but still they need to be signed by the service, and they are signed once and served from there on from S3. Another of our goals, which we are achieving with this system, is reducing the load on configuration management. So we drastically reduce the load we are putting on our DMs by shaving off this portion of their responsibilities. The service is highly available and elastic. Service itself is written in Go, runs as a Kubernetes, as a distributed Kubernetes cluster, and it's load balanced across multiple instances. And as like the extreme failure case fallback, we do put a copy of each boot artifact for each node in a public cloud S3, and the nodes will pick up their boot artifacts from here if they are unable to reach out the boot service entirely. And perhaps one of the biggest changes in terms of performance for this new system is that local boot strategy is meant to adopt a push model, where the artifacts are only rendered and updated when we know that there was a change to the node configuration that needs to be propagated down to the nodes themselves. And now I'm going to hand over to Matt to talk about future work on this area.
So we covered the history of the systems as well as the latest changes we've been making, but a systems engineer's work is never done, and we have more things that we want to do. So one of the things that we're rolling out right now is signing of the code that runs Cloudflare services. So we use Debian packages to deploy this, and we've implemented signing and verification using the Linux IMA subsystem for the Cloudflare service code that we run. We're also looking at eliminating the DMs. Joao talked about the chicken and egg problem and this bootstrap issue where the DM is like the first machine in the colo to come up, but where does the DM get its kernel artifacts from, or its boot artifacts? So eliminating that completely and having Metal's boot completely over the internet would drastically simplify this and also get rid of a number of corner cases. And lastly, we want to integrate TPMs. We have looked at this for a long time now. It's still on the roadmap of something that we want to do to extend that secure control all the way back to when you power on the machine. And that's it. Thank you very much for listening. If you have any questions, please don't hesitate to reach out to me or Joao. We love talking about this stuff. Thank you for your time.